Welcome to the third and final video in Unit 9 Momentum video series. In this last video lesson, we're going to talk about collisions, talk about what types of collisions there are, and then apply that concepts to some math. Before we can move on, it's important to make sure that we recall some very important information we learned in the first two videos. Let's look at that information now. First of all, we learned in video 1 that momentum, which has the variable p, is found by taking your mass times your velocity. We also learned that a change in momentum is most likely going to be caused by a change in velocity, provided that the system is closed. If the system is closed, that means no mass is being changed, and therefore velocity is the only thing that can actually be changed. If you want to change an object's momentum, we learned that you have to provide an impulse. An impulse was also defined, being the letter J, as the average force times the time that average force acts on. When you put those two concepts together, we learned about the impulse momentum theorem, which stated that the impulse, which is found by taking force times time, is equal to the change in momentum, which is found by taking mass times your delta V, or change in velocity. With these concepts in mind, let's go ahead and move on to this video, which is all about collisions. Now, up until now, we have been looking at systems where only one object is being analyzed. For example, in the previous videos, we've looked at, for example, a tennis ball bouncing off of a wall, or a car coming to a stop. All of these scenarios, we're only looking at one object, for example, the tennis ball or the car. In this video lesson, we're going to look at how momentum is changed when two objects or more are colliding with each other. In order to do this, we need to understand the idea of the conservation of momentum. When the system is closed and isolated, momentum is conserved. Let's talk about what that means. A closed system means that no matter can go in and out of the system. In other words, that means your mass is constant. The mass of our objects are not going to change. They're going to remain the same. Isolated means that all of our forces are going to be within the system, meaning no energy is going to enter or leave the system. It's all going to be retained. When both those things are happening, the momentum is conserved. Now let's look at that from a numerical standpoint. Let's look at ball A and ball B, and you can see that in the first scenario, they are sliding or rolling towards each other. Then they collide, and then after they collide, they bounce away from each other in the third snapshot. Okay, what we're going to do is we're going to apply some simple numbers to hopefully get the idea of this conservation of momentum. Before we do that, it's important that I establish a positive direction. I'm going to go ahead and say that to the right is the positive direction. Now, when we talk about an object's momentum, momentum is a vector quantity. It's a vector quantity because if you think about what actually makes up momentum, it's mass and velocity. Since velocity is a vector quantity, meaning it has direction, momentum itself must also be a vector quantity. So momentum will also have a direction. Okay, so knowing that, let's look at A and B. I'm just going to make up some numbers, some easy numbers, to hopefully get the point across. Let's say object A is moving with a momentum of 3 kilograms meters per second. Now, since ball A is moving to the right, and the right is the positive direction, its momentum is positive. Now, let's say ball B is moving to the left with a momentum of 8 kilogram meter per second. Since ball B is moving to the left, and left is established as the negative direction, its momentum is negative 8. And so if we talk about what is the total momentum in the system, positive 3 plus negative 8 gives me a negative 5 kilograms meters per second. This is the total momentum in the system. As long as the system is closed and isolated, that must be the momentum at the very end as well. So at the very end, let's say object A or ball A is now rolling and it has a momentum of 7 kilogram meters per second. Since ball A is now moving to the left, it is now negative after the collision. In order for momentum to be conserved, negative 5 has to be my total momentum in the system. And so what plus negative 7 is going to give you negative 5? The answer is positive 2. And so the momentum afterwards of ball B must be positive 2 kilogram meters per second. And notice that matches up. Ball B is now positive because it's moving to the right. This is a very simple idea of conservation of momentum, and it will prove useful in this video. Now, before we do the math, let's talk about two types of collisions. These are very general descriptions and definitions, but it will get us through what we need to know for collisions and conservation of momentum. There's two types. There's elastic and inelastic. Elastic collisions is one in which the objects are separate before and after the collision. So that's kind of like the one we just went over. Ball A and ball B were separate before the collision, beating up here, and then after the collision, they were separate as well. This would be known as an elastic collision. An inelastic collision we're going to define as objects that are sticking together either after the collision or before the collision. Now, what does that look like? Well, objects that are stuck together after the collision is something like, let's say two cars rear-end each other and they get stuck together. But what does a collision look like when they're stuck together before and then they separate? Well, that's like maybe having a loaded dart gun. The gun and the dart are together before, and then after the explosion or the release of elastic energy, they separate. We give this type of collision a special name. It's known as recoil. Whenever two objects are together at the beginning and then they separate, that is known as recoil. Okay, now that we know those types of collisions, let's look at the math. Conservation of momentum can look like this. P1 initial plus P2 initial equals P1 final plus P2 final. That sounds really complex and it looks really scary, but it's actually very simple. All that that's saying is the momentum of object 1 initially plus the momentum of object 2 initially added together must equal the momentum of object 1 finally plus the momentum of object 2 finally. This is just like the ball example that we did. If you recall, the momentum at the beginning for A was positive 3, and the momentum of B at the beginning was negative 8. So that would be positive 3 plus negative 8, and then we know that has to be equal to the final. If we go back and look at the final, A was negative 7, and B was positive 2. That's all that that's saying. Now remember, we learned that momentum is mass times velocity. And so you can see that the above equation with the momentum symbol just gets expanded to be included with the mass and velocity, but it's saying the same thing. So the momentum of object 1 initial plus the momentum of object 2 initial is just equal to what they are final. Now, this is the equation you will use if it's an elastic collision. You will use this equation if it's an elastic collision because the objects are separate before and they're separate after. You know they're separate because of the plus sign separating the two. But what if it's an inelastic collision where they get stuck? Well, let's take a look at those examples. For inelastic, take a look at this. The momentum of object 1 initial plus the momentum of object 2 initial, and then afterwards they actually get stuck together. You see, if they get stuck together, their velocity would be the same. So if we look at here, velocity of object 1 final plus velocity of object 2 final would actually be the same value. Why? Because they're stuck together. They have to be moving with the same speed. And so what we do is we factor this value out and we just call it VF. So if we factor VF out, we're just left with mass 1 plus mass 2 added together because the two objects would now be acting as one. If it's a recoil problem, notice how it's reversed. The two objects, mass 1 and mass 2, are together beforehand, and then they separate after the collision. Now, the inelastic equations that I've written here, these two inelastic equations, you can certainly use to make it easier, but this is the general equation that will work for every single problem. As long as you use this equation, it will work every single time. Let's go ahead and do some math so we can understand how to use this equation and really see how simple it is. Before we begin, a couple things to remember. The first thing you want to do when you read a problem is determine what kind of collision is it. Is it elastic or is it inelastic? Secondly, draw a picture. You don't have to be a perfect artist, just draw a picture. Thirdly, establish a positive direction. This is extremely important. If you don't do this, most of the time you will get the answer wrong. And then finally, number 4, write down your knowns and solve for your unknowns. With that being said, let's go ahead and look at this. The remainder of the video is 3 practice problems. Feel free to watch all of them or just watch the ones that you need. A 59-kilogram boy is on his 1-kilogram skateboard moving at 10 meters per second. He runs into another 63-kilogram boy on a 1-kilogram skateboard that's standing still. What is the velocity of the two boys if they stay together? Okay, step 1 says what kind of collision is it? Since it tells me at the very end that they stay together, this tells me that it is an inelastic collision. All right. Step 2 tells me to draw a picture. Like I said, it doesn't have to be a nice picture, but just something to give us an idea. So, here's boy 1 on the skateboard, and he's moving, and he's about to collide into another boy that's standing still. This is all initial. Finally, we know that they stick together. So I'm going to draw their skateboards close together, and perhaps they're holding on to each other, and that's why they're sticking together. But that's my final picture. Third step is I want to establish a positive direction. Now I'm going to make right the positive direction. And then finally, let's write down our knowns and our unknowns. And I'm going to do that right below the pictures. Okay, mass 1, which is right here. Be careful, the boy is 59 kilograms, but he's standing on a 1-kilogram skateboard. So that tells me the mass is a total of 60 kilograms. Mass 2 of the second boy is 63 kilograms plus his 1-kilogram skateboard. So that mass is 64 kilograms. Together, their total mass, I'm going to do total mass, since they are added together, they're now holding on to each other. That's going to be 60 plus 64, or in other words, 124 kilograms. All right, now let's write down their velocities. The initial velocity of boy 1, we are told, is 10 meters per second. Since he's moving to the right, and right is positive, I know that's a positive 10. The velocity initial of the second boy is 0 because he's at rest. We are asked to solve for what is the final velocity. Now that we know all of our unknowns and our knowns, let's go ahead and look at the equation. The equation is m1 v1 initial plus m2 v2 initial is equal to m1 v final for 1 plus m2 v2 final. Now, since they're stuck together, I know that these two v finals right here are going to be the exact same since they're sticking together. And so I'm going to rewrite the equation as m1 v1 plus m2 v2, all initial, is just equal to v final times m1 plus m2. Now let's go ahead and plug in my numbers, being very careful that I plug in the signs that need to be appropriate. Mass 1 is 60 times the velocity of positive 10 meters per second plus mass 2 of 64, although it doesn't really matter because it's 0. This is equal to the final velocity times the total mass together, which we know is 124 kilograms. If we simplify the left side, this value goes away since it's 0. And so 60 times 10 gives me 600 kilograms meters per second. This tells me that that is the total momentum in the system. So I set that equal to the final momentum in the system, which is V final of their combined masses of 124 kilograms. Divide both sides by 124, and that gets me my V final is 4.84 meters per second. As long as you stick with your signs appropriately throughout all the problems, the sign will come out correct at the very end. So for example, since I came out as a positive 4.84, I know that it is in the positive direction. And so after the collision, the boys must still be moving to the right. And if you think about it, that fits common sense. There's no way they would be moving to the left if they were to undergo that type of collision. Let's look at problem number 2. Two people on rollerblades are standing still facing each other. The mass of the first person is 65 kilograms, and the mass of the second person is 57 kilograms. They push off of each other and both roll backwards. The first person is moving a positive 2.3 meters per second. How fast is the second person going? Okay, first of all, what kind of collision is this? It's actually one of those special collisions. It's recoil, which is a special kind of inelastic collision. The second step is let's go ahead and draw a picture. These people are standing on rollerblades, and they're standing facing each other. Afterwards, finally, person 1 is going to be moving to the left, and person 2 is going to be moving to the right. Since it tells me that person 1, after the collision, is moving a positive 2.3 meters per second, I must know that the left direction this time is actually positive. Okay, finally, let's go ahead and write down our knowns and our unknowns. All right, I know that the first person has a mass of 65 kilograms, and the mass of the second person has a mass of 57 kilograms. Mass 1 over here is 65, and then mass 2 is 57. Now, their initial velocity for both of them is 0. And notice, because this is an inelastic collision, that's why they're stuck together at the very beginning. So I'm going to treat this side initially as being stuck together. Now, when they separate, I'm told that the velocity of the first person final is positive 2.3 meters per second. So we are asked to figure out what is the velocity final of person 2. Knowing that it's an inelastic collision and that specifically it's recoil, I'm going to use the equation where they are stuck together at the very beginning, and that's going to equal the mass of the first person and their final velocity plus the mass of the second person and their final velocity. Now, the nice thing about recoil is it doesn't matter if they're combined, what their combined mass is. Their initial velocity is 0. So that makes this go away. So if we rewrite the equation, we end up getting negative mass 1 times initial velocity of mass or person 1 is equal to mass of person 2 times their final velocity. Now we just plug in our unknowns. Mass of person 1 is it's 65 kilograms times their velocity of positive 2.3 meters per second is equal to mass of person 2, which is 57 kilograms, times their final velocity. On the left side, let's go ahead and simplify that. 65 times 2.3 times negative 1 gives me negative 149.5 kilograms meters second equals 57 times VF. Solving for VF, we divide both sides by 57. And so we end up getting, for a final velocity for person 2, is negative 2.62 meters per second. Notice how the negative is already in my answer because of the way I set the problem up. So long as you stick with your sign and write the equation correctly, you'll always have the correct sign. And notice that needs to make sense because if person 1 has a positive velocity, person 2 must have a negative velocity because they're going in opposite directions. Let's look at the third and final practice problem. Marble A, with a mass of 5 grams, moves at a speed of 20 centimeters per second. It collides with a second marble B with a mass of 10 grams, moving at 10 centimeters per second in the same direction. After the collision, marble A continues with a speed of 8 centimeters per second in the same direction. What is the speed of marble B after the collision? Okay, a lot of stuff going on here. First, let's identify what kind of collision. The marbles were separate before, and there's nothing in there to say that they would stick together. And actually, that makes sense. Why would marbles stick together unless they had some sort of adhesive on them? So, this is an elastic collision. Secondly, let's draw a picture. Here's marble A. And we're told that marble A has a mass of 5 grams. Marble A is moving with a speed of 20 centimeters per second. Now, it's going and heading towards the second marble, marble B. Marble B has a mass of 10 grams. And we're told that marble B is moving at a velocity of 10 centimeters per second in the same direction. So marble B must also be moving, but it's not moving as fast. So marble A is going to catch up to it, but they're moving in the same direction. So the velocity initially for marble B is going to be positive 10 centimeters per second. And let me put a positive back here. There we go. All right. Now, after the collision, so this is all initially. After the collision, we are told that marble A continues with a speed of 8 centimeters per second in the same direction. So this is my final picture. Here's marble A. Marble A is still moving in the same direction, and its final velocity is a little bit less now. It's 8 centimeters per second with the same mass of 5 grams. With marble B, what is the speed of marble B after the collision? So our final velocity for marble B is questionable, and its mass is still the 10 grams. All right, a lot of information to keep track of for sure, but just make sure you write everything down correctly. Now, they are elastic, so we're going to use my elastic formula, which is M1 times V1 initial plus M2 times V2 initial is equal to M1 times V final initial, V final, excuse me, and then plus M2 times V2 final. All right, now let's go ahead and plug in our information. We have 5 grams, and notice I can keep everything in grams and centimeters per second. I just have to make sure I know when I solve for my velocity at the end, it will be in units of centimeters per second. So I don't have to do any converting of everything because all my units will cancel out anyway, and I'll just be left in centimeters per second. So that makes it nice and easy. So I've got 5 grams is my mass, and it's moving a positive 20 centimeters per second. Plus the mass of 10 grams moving at positive 10 centimeters per second is equal to mass 1, again, is 5 grams, times 8 centimeters per second, plus mass 2 is 10 grams, times V2 final. And that's what we're solving for. Okay, let's go ahead and start simplifying some of that. 5 times 20 is going to give me 100 here, and that's grams, centimeters per second, plus 10 times 10, that's going to be 100 grams, centimeters per second, is equal to 8 times 5 is 40 grams, centimeters per second, plus my 10 grams times V2 final. If I clean up the left side, excuse me, that's going to give me 200 grams, centimeters per second is equal to 40 grams, centimeters per second plus the 10 V2 final. Let's subtract 40 grams, centimeters per second from both sides. And so that gives me 160 grams, centimeters per second is equal to 10 V2 final. Divide both sides by 10. That's 10 grams. That makes the grams cancel out there. And I end up getting V2 final, excuse me, V2 final is equal to 16 centimeters per second. And notice it's positive, so marble B would still be moving in the same direction. And if we go back, that makes a little bit of sense. Notice that marble A was originally moving 20, and marble B was originally moving 10. Well, now we've noticed that final, marble A decreased its velocity quite a bit, from 20 to 8. So we would expect that marble B would increase its velocity, going from 10 to 16. This concludes the video on conservation of momentum in collisions, and also concludes the video series on Unit 9, all about momentum.